Hello amigas and welcome into this new video in which we talk about audio and sounds in general. In electronic sound recording and output devices, the attributes of sounds are represented by the parameters of amplitude and frequency. Frequency is the number of cycles per second and the most common unit of frequency is the hertz, which is 1 cycle per second. The frequency of a waveform affects its pitch. Sounds with higher frequency are higher in pitch. Humans can hear sound between 20 and 20,000 cycles per second. The second parameter that defines a waveform is its amplitude. In an electronic circuit, amplitude relates to the voltage or current in the circuit. Since computers cannot store analog information, they use a finite string of numbers to represent a waveform. Each of these numbers is also called sample. The Amiga audio chip, Paula, can play sounds of 8-bit sample data. The Amiga has 4 audio channels. Channels 0 and 3 are connected to the left side stereo output jack, while channels 1 and 2 are connected to the right side output jack. Each audio channel includes a digital to analog converter driven by a direct memory access channel. The audio DMA can retrieve 2 data samples during each horizontal video scan line. When forming and playing a sound, we follow these basic steps. Define which channel to use, the waveform to reproduce, the length of the data, the volume, the sampling period, and then we can start up the DMA. Let's talk a bit about the waveforms now. These are 3 typical waveforms: the sine, triangle, and square. We can represent their data over time with these samples. Like graphics, music must also reside in chip memory, because, as we said earlier, the DMA must have access to it. Also, note that the first byte of data must start at a word address boundary. Each channel contains its own dedicated registers. We can store the address of the sample data into these contiguous registers with a move-L instruction. Volume can also be set on each channel and it's a 6-bit register. Thus, we can select a value between 0 and 64. The sampling period specifies the number of system clock ticks, or timing intervals, that should elapse between each sample fed to the digital to analog converter in the audio channel. By specifying the sampling period, we tell the system what frequency to use. If we have a simple waveform like the ones previously seen, we can apply the following formula to get the frequency target. We can then understand that the sample length affects the pitch the sample is played. From this table, we can see that in order to play a sample of a double sides with the same frequency, we must halve the period value. By the way, for complex sounds, we must know the original properties of the recording. For example, if we recorded a sample at 8000 Hz, we can apply the following formula to get the period value. Besides pitch, frequency also determines the duration of a sound. For simple waveforms, we can also get the fundamental frequency with the following formula. Let's do a concrete example to determine the time of a played sound. The minimum sample period is 124 for NTSC machine and 123 for PAL. The maximum value is 65,535. Minimum value limit can be explained because, in order to save buffers, the hardware is designed to handle a specific value of samples per second. The length of the data is the number of samples in your waveform divided by 2, or the number of words in the dataset. Please notice that the audio length, location and period are all backup registers. Backup registers are used to reload the working registers, which are actually an accessible register used by Paula to play sounds. This is actually a relevant information for us, and we'll know why later in the video. Now we can talk about the last step, which involves the DMA control register. In order to play a sound, we must set a 1 into DMA enable, the set clear bit, and the channel bit we want to enable. These are some examples of enable or disable sounds with DMA. We must keep in mind that once the channel is enabled and the start play sound, it won't stop until the channel is enabled. Once the DMA starts, the working register gets reloaded from the backup register. Also, an interrupt of level 4 is triggered. The interrupt will trigger at the end of the playback, and then again until we disable it from the interrupt control register. Let's dive into some examples right now. This example is about a generation of a steady tone with 3 different waveforms: a triangle, a sine, and a square. You can see we are feeding all the audio information into channel 0. On top of the source, I prepared some constants that are related to the period value for each note on PAL system. This was the triangle waveform. Let's play the sine. Finally, let's try the square. I saved the binaries of the waveforms from asm-one and then imported to Audacity. You can see the waves correspond to the expected shapes. In order to demonstrate the correctness of the formula frequency, I will import the raw sample data telling Audacity that were recorded at 8000 Hz. As you can see, Audacity imported the wave, resulting in a duration of 2.5 milliseconds. Now I will copy the waveform multiple times in order to get a 10 millisecond sample. And I let Audacity calculate the frequency. The next example, we show an audio property I have not talked at so far, the modulation. It's enough to know you can modulate the period or volume of a plain sample using an additional channel. In this example, I will show how to produce a sound formed by different waveforms. For this, I will enable the interrupt of level 4 at bit 7. Every time the interrupt is triggered, I switch the waveform between triangle and square. I recorded the audio and imported to Audacity to see the result. Okay, now it's time to try with a complex sound. because we want to get close to the real world. Okay, who recognized this? Please write a comment if you know what I'm talking about. On this snippet, we are not using any interrupt. However, we want to play this sample once. Remember that until enabled, the DMA plays the sample data continuously. The trick is, once the DMA is enabled, we wait some clock ticks with the equivalent of a raster line, and then we switch the channel data to an empty sample. We don't have to worry if after one raster line our sample is still playing. The channel working register will still point to the sample data, and after it finish, then it will be reloaded to the new empty sample. If you don't know how the CAA works, please check my previous video. This is a similar example, but this time we'll use interrupts. The interrupt is triggered immediately after the DMA is enabled, and after pointing to an empty sample, we also cancel the request and disable the interrupt. This is an alternate version of the interrupt. Here we don't use any empty sample. Instead, we use a switch flag. When the DMA enables and the interrupt is triggered, the switch flag changes its state. When the sound ends its cycle, we know from the switch flag that we can cancel and disable the interrupt and then disable also the DMA. Okay, now I want to debug some games, because I'm curious to know how they handled sound. I put a watch point on the channel 3 data location. This is the sample data of the fancy metallic sound we can hear during the menu. After some raster line, audio data location changed to another address. This is an empty sample. From the debug data, we can see we are in the same frame after 13 rasters from the start of the playback. For the first hurricane, I want to test the fire chute. This sound comes from the channel 3 again. Hurricane basically uses the same technique of speedball. This time, after one or two vertical blanks, the audio data channel points to an empty sample. Keep in mind that by disabling the audio channel DMA, we spare some cycle for other chips, like for example the blitter or the copper.
Prepare to die. Prepare to die.
This is the time for another old games called Barbarian. For this, I put a memory watch point on the channel 0. I was surprised to find that the debugger stopped at a kickstart memory level. I later recall that Barbarian actually used many libraries routines. After some surfing, I found out that this was the involved kernel routine. After reading the Amiga ROM kernel manual device, I finally managed on how to play sounds with audio device. Despite I would not recommend to use libraries for playing audio, the main advantage is that you don't have to worry about closing the DMA or playing the sound once. This is all handled by the audio device, which also allows to set the number of cycles for our sample. The last game I tried was Wizzball, another port from the 8-bit version. I was somehow happy to finally find a game that used the interrupts. I was also impressed to find how the developers managed the audio for channels. On this debug session, you can see the interrupt called the first time when the DMA is enabled. When the bouncing sound finishes its playback, the interrupt is triggered again. I was so impressed by the way the game manages sounds, so I decided to rip off the interrupt routine and replicate all the audio logic behind this. On this example, I first play two sounds at a different time. Before playing the sound, I set a flag which follows the proper bit of the DMA audio channel. For the second check, I will play two sounds simultaneously. The flag value is the sum of the two involved channels. The first time the interrupt is triggered, it only disables the flag. The second time the interrupt is triggered, thus the sample is finished, the routine will disable the interrupt and stop the DMA. Okay, we just hear the two validations behaving correctly. Okay, before concluding our video, let's take our good old spinning ball demo and enrich it with a bouncing ball sound. If you don't know what I'm talking about yet, please take a look to my previous video. I added a sound flag variable that acts as a switch. If its value is 0 and the ball touches the ground, the bouncing sound will be reproduced. At this point, sound flag will be set, and sound flag won't change its value until the ball leaves the ground. This is just a counter variable for this specific sound. A value of 0 means the sound playback is finished, so I can release the DMA. Notice that for the time being, we are not using any copper or blitter logic. So, in theory, we could leave the audio DMA enabled. For this example, I will not use the lever for interrupt, so the empty sample trick will do the magic. These are some validation about the position of the ball and the sound flag I talked earlier. This is where we play the sound. Once the DMA is enabled, we wait 2 raster lines so we are sure the working register is pointing to the bouncing sound. Sounds good. Thank you for watching this video, and if you liked it, please subscribe or put a like. See you next video. Bye!